This is video number 5 on revision for the chemical world topic for Year 9 Science, looking at atoms, elements, and the periodic table. So I thought I'd revisit writing chemical formulae for the first part of this video. So writing chemical formulae, so starting off with a name like magnesium chloride, how do you go from here to letters and numbers? The first step is to use your periodic table. Use what you're given. In every exam, you'll be given a periodic table. You're not supposed to memorize anything. Okay, maybe the valencies you're supposed to know off by heart, but the periodic table is all there. It's to write down the chemical symbols. Right, chemical symbols and valencies. Okay, of these elements. So recognize that magnesium and chloride, these are two elements, different elements, magnesium and chlorine. So Mg for magnesium, Cl for chlorine. Magnesium is in group 2 and it's a metal, so it has a valency of +2. Chlorine is in group 17, has a valency of -1. It's a non-metal. So magnesium, this is the cation. Chlorine, this is the anion. Step number 2 is to combine, stick them together. So the MgCl, Mg +2, Cl -1. Step 3, crisscross. Crisscross means bring the valencies down to subscripts. Okay, the valencies are superscripts, bring them down to subscripts. So MgCl 2, the 2 goes down, the 1 doesn't. Okay, the rule is only bring down numbers greater than 1. Not numbers that are equal to 1, or if you have plus some number and negative of the same number. So it could be plus 100, for example, hypothetically. There isn't any, but anyway, plus 100, minus 100. You don't bring any of them down because they cancel out. It's like me giving you 100 apples, then taking away 100 apples. You're left with 0. Compounds are neutral. This is a neutral compound. That's magnesium chloride. Let's do another one. Let's do lithium sulfate. Step 1, use your periodic table. Lithium. Now sulfate is a polyatomic ion. This is not on the periodic table. The elements are, but it's not on the periodic table. The formula itself. Sulfate, by definition, is SO4 -2. Lithium is +1. It's in group 1. You just have to memorize that. Sulfate, remember, sulfate is 2 words. Sulfur, S. Oxygen is 8. The 8, ATE, means oxygen. Step 2 is to combine. So stick them together. Step 3 is to crisscross. Li2, the 2 comes down from the sulfate, SO4, and the 1 doesn't come down. A lot of students still struggle with this. It's really not that difficult. There's just a couple of rules you need to know. Also, another way to think of it is you need 2 lithiums to balance the charge of the sulfate, which is -2, because +1 is +2, +2 -2 is 0, and this is neutral. So lithium is the cation, sulfate is the anion. In an exam, it's preferable to do this in one step, but you can do these on the side, okay, and then write your answer. Let's do another one. Let's do calcium carbonate. Step 1, periodic table. Okay, see how this is like a recipe? It's a series of steps. Okay, a couple of steps. Periodic table. Calcium is Ca, it's in group 2, so valency of +2. Carbonate, this is a polyatomic ion. You need to recognize this. Anything that ends in 8 is a polyatomic ion, most likely. By definition, it's CO3 with a charge of -2. Step 2, stick them together. You can do step 1 and 2 at the same time, but I'm just showing you the long way. Step 3 is to crisscross. In this case, you don't do anything because the +2 and the -2 cancel out. Okay, +2, -2 cancel out, give you 0. Let's do another one. Let's do ammonium nitrate. Now, ammonium and nitrate, these two are polyatomic ions. You have to watch out here. They're both polyatomic ions. By definition, ammonium is NH4+, because ammonia is NH4, nitrate is NO3 minus 1. Stick them together. Well, I'm not going to stick them together in this case. I'm just going to crisscross. You just get this. Okay, plus 1, minus 1 cancel out. I'll do one more. Vanadium 5 phosphate. Vanadium is a transition metal. And its valency varies, but in this case you're given the valency, it's 5. This is the Roman numeral for 5. Phosphate is a polyatomic ion. So vanadium is V, the symbol, charge of plus 5, it's a metal. Phosphate is PO4 3 minus, it's polyatomic ion. Stick them together and crisscross, you get this. The 3 comes down from the phosphate, PO4 brackets, because the phosphorus, the P, and the oxygen O are stuck together, 5 comes down. Let's now get into naming chemical compounds. So suppose I give you this, and I ask you to name all the chemicals here. What do? Well, you start from the left. By definition, this is hydrochloric acid. Because hydro means hydrogen, chloric means chlorine, HCl, hydrochloric acid. Plus, K is potassium, OH is hydroxide. Okay, if you separate these, you get K plus 1. Potassium is in group 1. Hydroxide is a polyatomic ion, charge of minus 1. Plus 1, minus 1 cancel out. Potassium hydroxide makes, K is potassium, Cl is chlorine, but it's not potassium chlorine, it's potassium chloride, plus water. Water is H2O. That's how you do it. Let's do another one. Let's do this. Okay, so it's nice to recognize what the reactions are. The first reaction was an acid, the base reaction, because hydroxides are bases, and oxides too, and they give you a salt, potassium chloride in this case, plus water. This here, let's find out what it is. So Cu is copper, CO3 is carbonate. Okay, when you break it apart, it's Cu plus 2, CO3 2 minus. When you crisscross, they cancel out, you get CuCO3. It's copper carbonate plus HNO3 is nitric acid by definition. Nitric is the nitrate ion, a polyatomic ion, which is NO3 minus 1. And all acids, the way I think of it, have hydrogen, so there's got to be a hydrogen at the front, plus 1. And plus 1 and minus 1 cancel out, you get HNO3. So you have an acid carbonate reaction that gives you a salt, which is copper in this case. Cu is copper, nitrate, NO3, plus water, plus carbon dioxide, CO2. Okay, it's like playing Where's Wally here, trying to identify the name of the chemicals. So that's how you name, you just look at the elements and you keep an eye out for any polyatomic ions. I'll now get into radioactive decay, radioactive half-life, I should say. So radioactive half-life is the time it takes for half the atomic nuclei of a radioactive sample to decay. Okay, I'll show an example, I'll do a graph. Suppose I've got this, days and percentage of element X. Actually, I'll do it down here, it's getting a bit messy. Suppose I have element X, could be something radioactive, doesn't matter what it is for now. And I have a graph that looks like this. This is what's known as a radioactive decay graph. So half-life in this case, so the way I think of it is looking on the y-axis, 100% of some element x initially at time 0. So initially, there's 100% of some element. The time it takes for it to reduce by half of 50 is half of 100, sorry, is 50. You read it off the graph, and that's about 2. So the half-life is 2 days in this case. It's the time it takes for the sample to reduce by half. Let's look at a table now. Suppose I give you this. Okay, excuse the mess. I'm not a perfectionist, that's for sure. Suppose you've got some radioactive element X and it's decaying over a certain amount of time, in this case, over the course of some days. Amount of element X in grams, so if it goes from 200 all the way down to 0, actually what I should do is remove some of this. Let's go up to 8 days. Now in a table, if you're asked to graph this, what you do is, typically the first column that goes on the x-axis. That's the independent variable, and on the y-axis, that's the dependent variable. I'll put it here, y-axis. On the y-axis, the dependent variable, that's the thing you're measuring in the experiment. In this case, the amount of element x left. Okay, what's changing is time. That's the independent variable. It's on the x-axis. Suppose I ask you to make a prediction as to how many days you would find none, 0 grams of element X left. Well, you'd see what the trend is. The trend is it's going down by 20 grams every day, right? So tracing down, predicting, okay, forecasting day 9, there'd be 20. Day 10, there'd be 0. So the answer is 10 days. So students were confused about this. The idea is just to forecast. Look at the trends, look at the patterns, what's happening on the right, in the right column. It's going down by 20 grams, so keep going down, and the number of days is going up by 1. And similarly, just add 1 day to each row. Now, just a bit of a side note here in terms of radioisotopes. So radioisotopes, write it down. Radioisotope is an unstable isotope. It's radioactive. It's an isotope which releases radiation. It could be alpha radiation, beta radiation, or gamma radiation. And there's many uses from medicine all the way through to industry. They can be quite valuable elements. So radioactive elements, these are the actinides on the periodic table. They're a particular row at the bottom. In medicine, you've got things like cobalt-60. Okay, that's used to treat cancer for radiotherapy. Iodine-131, it's also used in things like locating brain tumours and cancers. Industry, you've got things like sodium, Na-24. That's used to detect leaks in pipes. You've got iridium-192. It's used in detecting defects in materials. They've got their pros and cons. So radiation, obviously, in large amounts can be quite harmful to human beings. It can damage DNA. But in small amounts and controlled amounts, it can be quite valuable. It can kill cancer cells, for example.